show problem fixed parameter tractable. And we have also seen the notion of hardness in the parameterized world, W1 hard, W1 complete, W2 complete, and so on. But let's understand what this hardness notion means, right? So, in your algorithms course, you would have learned some lower bounds. Did you learn some lower bounds? What did you learn? Right. So, you learn that sorting has an omega n log n in the comparison based world. What else? So one of the things we want is that when we are designing better and better algorithms, lots of algorithmic tools, but we need to know whether we've reached the limit. Can you do better, right? So what else? What other kind of lower bounds you see? For example, you can very elementary kind of problems, min and max, if you want to find, or max. If you want to find max, you have a lower bound of n minus 1 comparison, but if you want to find a min and max, then you have a lower bound of something like 3n by 2 minus comparisons. You can, have you seen this anybody? Okay, so they're using adversary arguments. One can show that there are problems for which you need at least, these are in some sense restricted kind of lower bounds, because it talks about comparison based kind of things. What other lower bounds have you seen? Parity of a string using some circuit lower bounds kind of things, right? Okay, some parity which says that if you have bounded depth, then you need exponential size or things like that. They all come with some caveats. Okay, but what else? Anything else? Like any other kind of lower bounds you've seen? Okay, what else? I'm still okay, all that, but what kind of lower bounds have you seen? The whole notion of NP hardness is all about lower bounds, right? Right. So this notion of NP completeness or NP hardness, which says that under some assumptions, all of them come with some caveats, that under some assumptions, certain problems, you need super polynomial time. Right? This notion of NP hardness gives you a way of giving lower bounds, right? So this shows that n to the omega of constant, right? I'll just say I don't know. I'll say super polynomial. Under the assumption, what is the assumption? P not equal to NP, right? And then in this course, you have learnt this notion of W hardness, which says that no f of k into the c kind of an algorithm, under the assumption that W1 is not equal to FPT or W2 is not equal to FPT, depending on the kind of problems you're talking about. Okay. But let's look at this NP hardness. It's just, so let's pick some canonical problem like SAT. Okay. So SAT is NP complete means that you don't expect a polynomial time algorithm to solve it. But what kind of algorithm do you know? Right? So in terms of algorithms for SAT, the best known algorithms essentially take 2 power n time. Run through all possible assignments for your n variables. Maybe save some, maybe 2 power n, a fraction of 2 power n. Okay. For example, there is no 1.999 power n. We don't know. Right? But something like minimum vertex cover, we do know something better than 2 to the n, right? You know, in your probably about third or fourth lecture, we quickly saw something which was like 1.3 power n. But, you know, so there is, so we do know something better than 2 power n for a certain NP complete problem, but for certain other NP complete problem, we don't know anything better than 2 power n. NP completeness simply says that you don't expect polynomial time algorithm, but what about, you know, 1.3 power n algorithm for SAT? What about, and we, for example, we saw using bidimensionality and some excluded tree theorem, various other machineries throw at it. If I want a planar vertex cover, I told you can actually get 2 to the order square root of n kind of an algorithm. Okay. So, while NP completeness just rules out polynomial time algorithms, but beyond polynomial time, there are a lot of different timings possible, and NP completeness doesn't say anything about it. So, it will be nice to say, for example, that you cannot do SAT better than 2 power n. 2 minus 1.99 power n is not possible. We don't know. It will be nice to, I mean, you can't actually prove that unconditionally, right? Why not? Suppose I manage to show somehow that SAT cannot have 1.999 power n, then P not equal to NP, right? Because you've given an NP complete problem and somehow you argued there is not. So, you don't expect, I mean, you can, but then you would have, you'll become very famous. 3 SAT on the other hand, I think even this we saw, has something better than 1.5 power n. That if you, every clause has at most 3 variables, then there is something better than 2 power n. Okay. So, here I can ask the question, can I get better than 2 power n? Here I could ask the question, you know, is there a limit? Can I just keep going? Can I get an algorithm of this type for the standard vertex cover? You know, I can ask, is this the limit? You know, for, so all these questions are still open. This NP completeness doesn't say anything about it. Okay, it'd be nice to understand something about them. Okay, and let's come back to this W hardness. The same story here. We know that dominating set or clique or independent set, these are all hard. So, I don't expect, right, an algorithm which is some f of k times n cubed kind of algorithm for clique. But what about the best known algorithm? We have n power k kind of an algorithm. Can I get n power polylog k? What is the best f of k you get, right? For vertex cover, we get 1.2 power k, but can I get 2 to the order root k, right? There are all these questions, so which are interesting and we don't know much about. So, for vertex cover, can you get 2 to the little o of k? And for clique, can I get n to the log? We know there is no f of, you can't get f of k n to the c, but can I get something like, so all these questions are interesting. And it turns out there is a whole lot of results one can show with some assumption we have to start with, because as I said, you know, I unconditionally, if I argue, if I manage to show anything, I would have shown something about p not equal to np. So, let's make some reasonable assumption under which we can show some of these results, right. Now, this assumption, well, what is a reasonable assumption? And so, there are two important hypotheses which are known, sort of standard. One is the exponential time hypothesis, and there is something called strong exponential time hypothesis. Okay, so this is ETH. Exponential time hypothesis says roughly that if you talk about 3 sat, that there is a C. Okay, another way to see it is that there is a C such that no 2 power Cn algorithm. Right? You can't just bring the C as small as possible. There is a constant beyond which you cannot get something better than that for 3 sat. And strong exponential time hypothesis says that the standard sat or it actually says something about Q's. Yeah, maybe I'll just write it in the more popular thing. For any epsilon. These are hypotheses because we don't know a proof, but some sort of a conjecture. Like SAT cannot be solved in polynomial time, but this is making little more precise kind of a time bound. It says that SAT cannot be solved in 2 minus epsilon, and exponential time hypothesis that you cannot get 2 power little of n. How justified are these assumptions? Well, we don't know. Maybe these are wrong, that's okay. But somehow we can start with the assumptions, give some reductions, and prove some interesting lower bounds for a whole lot of problems, which are super polynomial lower bounds. Instead of simply saying no polynomial time, we can say you can't get to power this kind of an algorithm. And that's a whole lot of interesting results by themselves. And another way to see these results, so suppose based on all of this, some of these are immediate. Once you have this assumption, often you can use the NP complete reductions itself and try and deduce that, oh, this implies that vertex cover cannot be solved in 2 to the little of n time. Dominating set cannot be solved in 2 to the little of n time, and so on and so forth. You just say if it is, then you can solve this. If the reduction maintains some interesting properties, then that's good enough. But how justified are these assumptions? Well, how justified is this assumption that P not equal to NP. Another way to think about this, that if I want to disprove this, suppose I want to show P is equal to NP, then every NP complete problem is useful for me, right? Because this reduction, so I can pick any one of the NP complete problem and try and give a polynomial time algorithm. I would have shown P equal to NP. You can also think of these results as that if I want to disprove this, instead of working on 3 sat, I can work on any of these problems to which 3 sat reduces in reasonable time, and work on any of this and give a 2 to the little of n. So, you just extend the domain of problems in which you can work on to disprove it. That is another way to think of these reductions. Okay, you can think of it as, oh, that this is a lower bound for the problem under this condition, or If you want to disprove this, then you have a variety of problems to work on. Okay. So today I will just talk about some results based on ETH and ACTH. I will not give any specific reductions, but I'm just going to give you a whole lot of interesting results known. And it's already interesting that SAT and 3-SAT have a different kind of a behavior. Okay. Yeah. So now, one natural question is, SAT reduces to every NP-complete problem. So that in polynomial time, then does it not immediately follow that if SAT cannot be solved in 2 minus epsilon whole power n time, then no NP-complete problem can be solved in 2 minus epsilon power n time. Of course, I have some examples to show that that's not the case, right? Because SAT can be solved in 2 power n, cannot be, we don't know, but 3-SAT can be solved in 1.5. So what's happening, right? So here is my argument. Tell me what the flaw in this argument is. I'm just saying, so I have SAT in poly time reduces to your favorite problem, vertex cover. Okay. So you should be able to use your efficient algorithm for vertex cover to give an efficient algorithm for SAT. So why is it that vertex cover can be solved in 1.3 power n, but SAT cannot be? Exactly, right? Did you follow? No. So what happens here is SAT has n variables and m clauses. When I get to a vertex cover instance through a polynomial time reduction, I get a graph G where the number of vertices is some polynomial in n and m. So this could be like an n cubed, right? So now if I apply my 1.3 power n algorithm here, n is actually n cubed. So it's 1.3 power n cubed algorithm. That doesn't give me anything 1.3 power n here. Okay. So the moral of the whole thing is that now now you want to find some nice tight reductions. That's all the story is about, right? So this whole notion of reduction you would have learnt in complexity theory, that sometimes you want in the NP completeness reduction you are happy with only polynomial time. When you talk about parameterized reductions, you allow exponential in the parameter, but you want to make sure that the parameter goes to the parameter. You could talk about log space reductions. So it's not just polynomial time, but the space for the reduction should be log space. You could talk about linear reduction where the n should go to order n here. Okay. If you have linear reduction, then at least on the sub-exponential world you can play the game, right? So you can say that, so suppose I have a linear time reduction from 3-SAT to vertex cover where the parameter n goes to some Cn. Okay. Then sub-exponential 2 power little of n algorithm for vertex cover would immediately imply a 2 power little of n for 3-SAT. Okay. And there are standard NP complete reductions have that feature. So at least for some of the problems. So immediately from that reduction and exponential time hypothesis, you can deduce a lot of things. Okay, so let me just write down what we know. So for example, so I'm going to now not just So what kind of lower bounds can we derive assuming this? So result 1, assuming ETH, we have vertex cover, feedback vertex set, Hamiltonian path, dominating set cannot have 2 to the little o of n. Oh, okay. Before that, I have to say something. No, I have to tell you something about the m in the formula. Yeah. So vertex cover, dominating set, feedback vertex set, 3 coloring. Let me add that. I'm going to keep using this. All of this standard NP complete reduction. But there's one little thing I have to deal with. Yeah, the standard NP complete reductions, I'm not going to do them, you can just look up. What they do is they reduce from 3 sat to any of this problem, let's say dominating set. This has n variables and m clauses. It reduces to some linear, but not just on the number of variables, but also on the number of clauses. Okay, this is what I need to this is not quite the proof of this because of the m in the thing. Okay, but I'll spend some time talking about it now. But if it is all like this, then you are fine, right? If you had a reduction which takes n variables 3 sat to some order n vertices, then what is the proof of this? Suppose this dominating set has a 2 to the little o of n algorithm, then you apply it and you will get 2 to the little o of n for 3 sat, disproving ETH. So, if you assume ETH, this follows if I had n going to some order n, right. So, but these guys will actually have typically order n plus m. So, how do I deal with it? Now, I do not want to deal with it because somebody else actually dealt with it. There is this famous lemma called sparsification lemma, which relates the number of variables and number of clauses. So, in particular in 3 sat, how many clauses can there be? There are n variables. If there are n variables, then how many clauses can there be? Order of n cubed, because you just take any 3 out of it, and but once you pick 3 out of them, there are 8 different clauses you can get out of them. That's still about 8 n cubed clauses you can get, right? So this m can be as bad as n cubed. So I don't like that in this reduction, because then this 2 to the little o of n doesn't translate to 2 to the little o of n, because n is not n plus m. Okay. So what we will do is apply this sparsification lemma. So this is the due to Paturi, Podlek, and one more person. So what do they say? What they say is the following: for all epsilon greater than 0, for all q, any QSAT formula phi can be written as R of psi I equal to 1 to t such that t is about 2 to the epsilon n and each psi I has at most some Cn clauses where the C depends on epsilon and q. And the phi i's can be found in so what would be nice is that if if this starting 3-SAT formula only has linear number of variables, when is the number of variables, linear number of clauses, then I can use this reduction, lift a little of an 2 to the little of an algorithm to 2 to the little of an algorithm, even if the reduction uses n plus m because m is order n. Okay, but that I cannot guarantee, but the sparsification lemma says something close to that. What it says is, okay, I am going to allow you some exponential time to find. So, it is not just that formula has linear number of variables, but I can decompose it into some bunch of formulas. The number of different formulas is some 2 to the epsilon n. You choose your epsilon. I will come up with that many. So, epsilon can be very small, then I will have that many different formulas. Then solving testing satisfiability of phi is the same as testing satisfiability of all of these guys. The nice thing about these psi i's is that they have linear number of clauses. Okay. So, now what we will do to show, for example, the dominating set cannot have a 2 to the little of an algorithm under ETH. I will start with my 3-SAT, spend my 2 to the epsilon n time to find these psi i's. Right, I would have spent epsilon is my choice. Remember, it can be as small as possible. And then I have 2 to the epsilon n different formulas and test satisfiability on each one of them. Right. The nice thing about each one of them, they have only linear number of clauses. So, now what I will do is I will reduce each one of this to my dominating set reduction, use anti-complete reduction, that is only order n vertices now, because m has become order n. Apply my 2 to the little of n algorithm for each one of them and compose them together. Since epsilon is my choice, for any epsilon I can have an algorithm which is like 2 to the epsilon n time to test whether dominating set is no, if this can be tested in 2 to the little of n time, a test set for each reduced instance of each psi I to dominating set, and overall I will be spending 2 to the little of n time, or I will spend 2 to the epsilon n time for any epsilon you have in mind. Okay, there are some calculations involved, I am not saying it, but the importance of the sparsification lemma is that it just relates number of variables and number of clauses to be linear in the number of variables at an exponential cost, where this exponential is 2 to the epsilon n for any epsilon you have in mind. Okay, is the picture clear? So, now with that sparsification lemma and your reduction standard NP complete reduction, which takes n variables m clause formula to order n plus m vertices, you can show that this has 2 to the little of n algorithm. What is 2 to the little of n means? That for any epsilon there is a 2 to the epsilon n algorithm. I can apply that, compose it with that. This would imply 2 to the little of n for 3 sat, which implies that ETH is false. So, if ETH is true, then there is no 2 to the little n algorithm for dominating set, and you can show for all of these problems using the standard NP-complete reduction. Okay. The other thing is, why is one called strong exponential time hypothesis, another is exponential time hypothesis? In what sense it's, I mean, that one is stronger than the other. You expect stronger one implies the weaker one, right? And that is true as well because of all of this. So, yeah, I'm not again going to give a proof of this, but I'll just give you a flow of how it works, right? So, what is this saying? That in fact, we will say something stronger. 2 to the little of an algorithm for 3 sat implies 2 to the epsilon n algorithm for any epsilon for any q. So, then at the limit this would be 2 minus epsilon or even 2 to the little of n algorithm for sat. What is sat? When there is no bound on q, right? That is a sat. So, how do I show this? Well, you take a q sat instance, q is very large, okay, unbounded, apply sparsification lemma, and you get some linear number of variables, linear. So, if you again, if you look at the, if you remember your standard NP complete, the same kind of a problem. If you remember a standard NP complete reduction from q sat to 3 sat, you remember how it goes? Say 5 sat to 3 sat. So, suppose without loss of generality, this 5 class is this, and I want to bring it into a 3 sat. So, what do? X1 or X2 are some Y1, and then Y1 bar are X3 or Y2, and Y2 bar are X4 or X5. You write this and then you say that this is satisfiable if and only if this is satisfied. How many new variables have you created? Yeah, in general, q minus 2, exactly, right. In general, you would have created q minus 2 for each clause, right. Now, if you have lots of clauses, then it is like q minus 2 times m. That is too much, but if m is order n, then it is okay. It is still a function of q and n, I can deal with it. So, I will apply sparsification lemma. So, what do I want to show? I want to show that if you can solve, yeah, that is what, this is what I want to show. If you can solve 3 sat efficiently, I can solve larger sat efficiently, right. So, what do? I take this q sat, first apply sparsification lemma into a whole bunch of things, some exponential number of them, right, 2 power epsilon n, but each one of them has linear number of clauses. So, now for each one of them apply that reduction. So, the number of extra variables you would have introduced will be like something like q minus 2 times Cn for each of these clauses. Now, for that you apply your 2 to the little o of n algorithm, then this little o will blow because now there is a multiplicative factor of q, but you choose your epsilons carefully in a way that, you know, there is an epsilon here, choose them carefully, that with all of that you achieve, you know, 2 to the epsilon n algorithm for q sat for any epsilon you have in mind. Because if for this epsilon, when you get to 3 sat, you want to choose a much smaller epsilon, so that even with the multiplicative factor of q, it all works out fine. Okay, so that's the high level picture of how you show this. Okay, so the strong exponential time hypothesis is really strong. Okay, I told you this today is all about some stories, may not be real proofs. Right, now let's get to something like planar graphs. Okay. So here, for example, from SAT to typically planar vertex cover or something, or let's say planar dominating set, right? And I said in the general world, you have n plus m going to order n plus m, right? Here the story is slightly different. You have n plus m going to quadratic. The standard reduction. How do they do? Again, a big picture level. So there is a notion of planar SAT. What is planar SAT? Right. So what you do is you have this incidence. This is clauses. This is variables. You take your SAT formula. Okay, standard SAT formula, CNF SAT formula, and you have a vertex for every clause and vertex for every variable, and you draw an edge if this variable appears in that clause. Okay. If this graph is planar, then we will call that SAT formula planar SAT. Okay. So now what people do is that you reduce from standard SAT to planar SAT, where is n plus some. So I am going to now actually say n because of all this sparsification lemma. You can make it linear with the penalty of exponential time. So this n becomes n square here. Okay, and why? How do you do it? If the graph, so you take a standard SAT, it may not be planar. So wherever there the thing cross, right, there is an edge. So why is it not planar? Because this edge and this edge cross. Here I will add some gadget here, and maybe make it planar. Okay, some constant size gadget. Now, how many crossings can there be if there are n vertices? N square, right? And every pair can. So if there are m edges, there could be m crossings. So that's why when you add this constant gadget for every crossing, this n becomes n square. And then you start from your planar SAT to reduce to planar DOM set. Here you maintain your linear reduction. So then from SAT to planar dominating set, your n becomes n square. Okay, the standard NP complete reductions. So now using this n to n square reduction, what can I say if I want to assume ETH? So I want to say, suppose, right, I have a reduction which takes a SAT on n variables to the planar dominating set, but it makes the number of vertices n square. Then ETH implies what? Right, because 2 to the little of square root of n. Right, in fact, even initially I said if n goes to n cubed, then this 2 to the little of n doesn't help me anything, but something helps me. So if, for example, planar dominating set can be solved in 2 to the little of root n, then I can apply that to this reduced graph my, let us actually call it capital N. This capital N is n square. So, I will get a 2 to the little of n algorithm for SAT. Okay. So, I can get only something like a weaker statement, right, because 2 to the little of n is a very strong statement, but I obviously won't get 2 to the little of n, because if you remember again, we actually solved planar dominating set problem in 2 to the order root n time using bidimensionality, grid theorem, which says that if you have a large grid, the requirement is large. And so, in planar graphs, using bidimensionality and grid theorem, last week we saw many problems, vertex cover, feedback vertex set, dominating set can actually be solved in 2 to the order square root of n time. So, this tells you that that is more or less optimal, which is very nice, right, because unlike saying, oh, non-polynomial time, this is saying even something very tight, of course under ETH, right. So let me write that we have seen so all of these are optimal. Really, this is nice because it just gives you exactly this tight bound. So, this 2 to the order root n algorithm, recall again it used the fact that if you have a large tree width, then you have a large grid has a large dominating set, the answer is no. So, you should have a small tree width, and in small tree width you can apply the standard dynamic programming and get to the 2 to the order, that is the algorithm. Okay. Sometimes we had 2 to the order root n, sometimes we had root to the order root n log n or something. So, it is optimal with that little gap. So, this is nice. So, it shows that if you make the stronger assumption rather than NP completeness, you can actually get some stronger results for some of the, okay. So far I have not talked about parameterized problems, and we looked at only this optimization problems. When you come to the parameterized problem, some of the results immediately carry over. So, for example, parameterized VC cannot, if he has how does this follow? So, here the question is there a k size vertex cover? What happens if I have a 2 to the little of k algorithm? I mean, you can try out various values of k and you will actually get a 2 to the little of n algorithm for a vertex cover, the optimization problem, for which I already shown that under ETH that is not possible, right, because and similarly for planar graphs, 2 to the little of square root of k is not possible. Okay, now turns out you can even show something stronger lower bound. There are problems for which you only had something like k power k algorithm, not even c power k, and you can show that optimal under ATH. So let's pick one problem, and that is a good reduction which I will do carefully because we'll use it later on also. So here is yeah, so this is a multicolored click. So what's the input? So a graph. I'm phrasing it in my way. So n is k square. And the question is there a k click? A multicolored k click. So you can think of it as my graph looks like this. So this is color 1, color 2, color k, and each one has k vertices. So the graph has k square vertices. And is there a click which picks one from color 1, one from color 2? And so the edges across are arbitrary. And the question is there a click on k vertices where one vertex comes from C1, one from C2, one from CK? And our parameter is k. And each color class has k vertices. So what would be like a brute force algorithm? K to the k, right? So there are k to the k choices. There are k choices for C1, k from C2, and so on. Pick one such k tuple and check whether it forms a click. Try all things. So it's like a k power k into k square or something to check my adjacency matrix to see whether those vertices I picked form a click. So it's not even c power k. Some very simple, sort of like an artificial problem maybe. It's a click problem, but with some special instance. And we will show that this is sort of optimal. Okay, you can't get unless under ETH. The claim is that 2 to the little, so this is 2 to the k log k, right? No, not 3 sat, 3 coloring. Okay, so why am I saying all of this? In general, when you have a problem, you try and show it's NP complete. You try and show it's W1 hard. You come up with some exact algorithm, FPT, whatever, and you may want to show that there is no 2 to the little o of n algorithm for that problem, right? So you need a way to say that. That's a very strong result than saying no polynomial time algorithm. Like it's instead of saying just NP complete. So this is an extra toolkit, this kind of reductions, which helps you to show some additional results, which okay. And also for super exponential lower bounds, this is like a, even though this problem may not be very interesting, but this could be a good starting point to do your reductions. Okay, so we will show that if you have such an algorithm for this problem, I'll show that for an arbitrary graph, I want to test 3 coloring. I can do it into the little of an algorithm, and this I have already told you that this would imply SAT can be solved in 2 to the little of n time. So under this assumption, this, I mean, if you believe in ETH, then you cannot get such an algorithm. That's what this says. Okay, so now what is my goal? To design such an algorithm and using this assumption. Okay, so I have given an arbitrary graph and I want to do some 3 coloring, right? So my k is going to be n over log n, some order n over log n. So let's see, what do I have to do? Let's understand at a high level. I'm going to reduce this problem. So kernel B is n. I want to reduce it to what? If I want to use this algorithm, what do I have to do? I want to use a 2 to the little of k log k algorithm for this problem to design a 2 to the little of n algorithm for 3 coloring. So what do I do? So from this problem, I want to reduce to this problem. This problem has k square vertices, k colors, everything is nice. So and I am looking for a k cliff. So the only thing that I need is k. So what should be my k? So that a 2 to the little of k log k for this would translate to 2 to the little of n. Well, essentially k log k has to be n. So what should be k? Roughly, yep, n by log n, right? So that's what it's going to be. So modulo some constant. So we'll figure out what that c is and so on. So that's a starting point. If I want to do this reduction, I want k to be c n over log n. So I have this k groups, right? So I'll partition V into c n over log n groups of c log n vertices, log n by c vertices each. C is a parameter which we will determine later. Okay. So, I want to solve 3 coloring and I am given a graph and I take my vertex set and partition it into some log n by C vertices each and number of groups, so it is going to be C n over log n. Okay, now I have to come and give you a k square sized vertex set, so that a click here would correspond to a 3 coloring and vice versa. That is my goal, right, because now I have to come give you a k square size graph with these colors, so that a k click here would correspond to a 3 coloring and vice versa. Okay, how many possible 3 colorings are there? For a group. So each group has, let us say, G equal to log n by C vertices. Number of possible 3 colorings for that induced subgraph on G vertices. In general, if for a graph on n vertices, how many possible 3 colorings are possible? 3 to the n, right? Because each one, some of them may be not a proper coloring at all, you throw it away, but maximum there will be 3 power n colors, right? So, that is now if there is no 3 coloring for that group at all, you can just stop and say no. Okay, I have to tell you about how much time I am spending on this. Yeah, hopefully that is another thing. For this reduction, I should be spending time, something like 2 to the k or something. That is what I will do. Right? So, we will come back to the timing for the reduction. Remind me about it. So, I will have, so this is group 1, group 2, group k. So, k is going to be my C n log n, right. So, this is my group. So, this group has some log n by C vertices. So, now each vertex here for me is a 3 coloring of vertices in G1. So, maybe lots of 3 coloring. So, I will have lots of different vertices. Okay. And if there is no 3 coloring at all, I can stop and say it is a no instance, because my problem is to solve the 3 coloring problem. Along the way, I did not find any 3 coloring for even for this little group, I will say no. Good. I want k by k partition, right. So, this 3 power j g should also be equal to k for to fit into my input description. So, let us choose. So, what is 3 power g? 3 power g is 3 power log n by c. Okay, to use a description, let me just say log n to the base 3 for all you care. How does it matter? So, to make life easier. So, this is log n to the base 3. So, this is what n power 1 by c, right. And this is clearly less than or equal to C n by log n as long as C is greater than or equal to 2, asymptotically, right? Otherwise, n has bounded number of vertices, you can do some brute force. Because if C is 2, this is like root n, this is n over log n, so asymptotically this is much larger than this, except for some small values of n. If n is in that range, you just answer the question brute force. Okay. So, the number of vertices here, the way I have written, is less than or equal to the number of groups. I want it to be equal really, so I just copy some coloring, right, make it equal. So, now I have here, right. So, repeat some 3 colorings so that 3 power g or whatever the number of colorings is equal to k, which is equal to Cn by log n. Because it's usually less, so I repeat some, so that now I have k square. So, now I have given you a graph with k square vertices, and each vertex is a 3 coloring of this group. Okay. Now, I have to tell you how the edges are drawn. How do you think it should be drawn? Compatible coloring, right. So, I draw an edge between a vertex here and a vertex here. This corresponds to, so here is my set of vertices here. This corresponds to a 3 coloring of this, and this corresponds to another set of vertices and a 3 coloring. Now, there may be, so they are all using the same 3 coloring 1, 2, 3. There may be an edge between here and this may be color 1, this may be color 1. If this happens, then that's not a compatible coloring. But if these 2 colorings, if you put together, is a compatible coloring for this union of these 2 groups, then I draw an edge. Okay. So, a picture of it. So, draw an edge between V in Gi and U in Gj. If V and U are compatible 3 coloring for the vertices in Gi union Gj. Okay, good. So, now it should be easy to see that now the claim is, so let us call this graph G prime, then G has a 3 coloring if and only if G prime has multicolored K clique. So, let us just quickly see a proof. If G has a 3 coloring for the original graph, then there is a coloring for each group of vertices. So, just project that overall coloring to each group. Now, this coloring and that coloring, this coloring, all that would be a compatible coloring, and you will get a K clique with all different colors, one from each group. Conversely, if you have a K clique here, then this and this and this and that is a compatible thing, every pair of them. You can lift back a 3 coloring for my original set of vertices. Okay, and how much time did we spend to get this? So, reduction time is essentially the number of vertices right, because some times some polynomial thing. Reduction time is each one, what do? I take this group and give one coloring, and then I have to check whether it's actually a coloring. So, there is some whatever the size of the group, G square time. And I do it for each of this coloring. So, it is a number of vertices into some G square. And what is the number of vertices? Yeah, k is like Cn by log n, right? I mean k square. So, it is like an n square by log square n times. No, what am I saying? Number of vertices would, yeah, so each time. Oh, I also have to draw edges. Okay, I missed that. So, whole square. So, I am going to just say k power 4. But it is still some polynomial time. K is like n over log n. So, you are spending polynomial time. Okay. And if you have a 2 to the little o of k log k time here, k log k would be n over log n log k, which would be like n. So, this follows. So, this is a nice example where even a super exponential running time is optimal. There is a even better, I mean under ETH of course, is even better super exponential lower bound is shown to be optimal. I'll tell you the problem because the problem is interesting. It's the edge click cover problem. So, the input is graph G. How much more do I have? And there is a parameter k. The question is, yeah, can we partition the vertex set? No, not even partition. Are there k clicks? These need not be disjoint that cover all edges. Okay. So, for example, if this is my graph, then I have like 2 clicks that cover all edges. Right. So, this is one click and this is another click. Okay, in the second click, yeah, I have to have all this. So, this clicks can intersect, vertices can appear in more than one click, edges can appear in more than one click. These are different clicks. And the question says, can you come up with k different clicks in the graph that will cover all edges? Problem clear, right? So, vertex set, edge set can overlap, but the clicks are not necessarily disjoint, but I just want edges to be covered by clicks. There is a very simple kernel for this problem. Let us think of some reduction rules. Actually, this is one real reduction rule. Okay, let us assume there are no isolated vertices in the graph. They are not having any edges. So, now here is a rule. Degree 1 vertices, what do you want to do? Okay, if you have a degree 1 vertex, that edge must be in a click. So, what do you want to do? Can you delete it? Yeah. So, you remove that edge and the isolated vertices. Yeah, sure. Yeah. Okay, so here is a very simple rule. Suppose two vertices of the same neighborhood close neighborhood. Let us say U and B. What can you do? Delete any one of them. Why? So, let us call them as twins, right. So, if I delete any one of them, suppose U and V is a twin, I deleted U. Now, I formed this K click, or maybe it is a no instance, suppose it is an S instance for the reduced graph. Now, I have to insert U. Where do I insert it? All the clicks V is sitting there, just go and insert U. Okay. Since V and U have the same neighborhood, when you insert U also, all of them will be a click, number 1. And all edges incident to U must be covered also. Will they be covered? Yes, because all edges incident on V are covered by these clicks, and U and V have the same neighborhood. So, if whatever edges incident on V are covered, this attach U to all the clicks V belong to, you can cover that also. So, now you just delete this. So, whenever you have twins, just delete them. Okay. So, now after this, I claim that if n is more than 2 to the k, return no. Why? So, suppose it is an S instance. Okay. So, that means there are k clicks that cover all edges, k clicks of this graph. Now, for every vertex, I will write down a binary vector which tells you which are the k clicks it belongs to. Okay. Suppose not. What does that mean? That means there is an S instance. So, here is k clicks, not all disjoint. Now, for every vertex V, let us call this click 1, 2, 3 up to k. I write a binary vector which says 1, 1, 0, 0, 0, 1, 0, 1, 0, which means that V is in the first click, second click, sixth click, eighth click. I do this for every vertex. Okay. If n is more than 2 to the k, what does that mean? Two of these vertices have the same encoding. What does that mean? These two vertices belong to exactly the same clicks, which means their neighborhood are the same. This rule would have applied and you would have deleted one of them. So, in the after doing this, in the reduced graph, the number of vertices is at most 2 to the k. So, this is a kernel, not a polynomial kernel, but it is a kernel. Now, you have bounded n. Now, you do brute force. What is brute force here? Two vertices have same encoding and rule applies. Okay, so now brute force is you want to do partitioning of the edge set or partitioning of the vertex set, there are lots of choices. For every vertex, you can decide to k choices, put in any of the k clicks, right? It can be actually more than k choices. It can be in click 1 and click 3 and click 7 as well. Okay. So I would just say, yeah, I think even a 2 to the n algorithm exists, but it's not easy. So I'm going to say 2 to the n, which is at most 2 to the k. I'm going to say that if there are n vertices, if I want to solve it brute force, what can I get? I don't even know whether it's 2 to the order n or 2 to the order, or 2 to the n or 2 to the order n. Okay. So with the simple rule, not being very clever, we have a kernel and we have a 2 to the k FPT algorithm for this problem. One can show that under ETH, there was a paper about 4 years ago which showed that this is optimal. Okay, and what they showed is they reduced from 3 sat on n variables m clauses to this problem where n is like log n. Okay, you have a log n number of vertices and you want to do this edge click on that set of things. So 2 to the n, or 2 to the k little o of that would give you 2 to the little o of n algorithm for sat. Okay, so I'm going to say under ETH, okay, so I think I will stop here. So using, for example, this 3 coloring to click example, one can show that click cannot have n to the little o of k algorithm. So I'm going to say other results. More or less the same reduction. You need to be a little careful about the group sizes and so on. That if I, we know click is W1 hard, so you don't expect an f of k n to the c algorithm, and we already know an n to the k algorithm. But what this is saying is I can't get an n to the root k algorithm under ETH. Okay. Okay, so I think I will just stop here. This is just a flavor of different kind of results by making this stronger assumption about SAT, that you can't solve it in 2 to the little o of n time. We knew all along that you can't solve it in polynomial time unless something happens. You make this little stronger assumption, you can prove some whole lot of stronger results on the exponential exact optimization problems as well as on the parameterized problems. So here are examples of parameterized problem which is FPT, but you can show that the FPT bound is optimal. Here is a problem which is not FPT, you have W1 hard, but you can show that whatever XP algorithm we have is optimal. Okay? And this is sort of a flavor of results under making this assumption about ETH. And I didn't even get to talk about strong exponential time hypothesis, because any reduction based on that is even harder. Because if I want to show that a 2 minus epsilon and for SAT would mean a 2 minus epsilon or 2 minus epsilon n for some other problem would imply 2 minus epsilon n for this, the n really has to go to n. I can't even get a Cn reduction. Even if it's a linear bound, I can't get a 2 minus epsilon n to So n really has to go to n or n plus little of n. So any result based on set is much harder, but there are some results now. Okay, there's a whole chapter in the book about ETH, SETH based lower bounds, and I sort of covered about 50% of them in a high level. And tomorrow we'll talk about some kernelization lower bounds and